This is LeetCode 3542, minimum operations to convert all elements to zero. So in this problem, we're given an input array nums of size n, which consists solely of non-negative integers, and the task is to apply this operation to the array, so eventually all numbers become zero. Now, the operation in question is selecting any single subarray of the entire input array, finding the minimum number in that subarray, and then converting all instances of that to zero. And we want to return the minimum number of times that we have to apply this operation to end up with an array of all zeros. Now, looking at this example given in the problem, we have an input array of 3, 1, 2, 1. First, the first subarray that's chosen is a 1, 2, and 1, with the minimum element obviously being a 1, and we would set both instances to 0. And now, with the structure of the array, you can see that 2 is the next minimum element that we can find, but there's no more instances of 2. So we can just select it as a subarray including one element and set that equal to 0. And then we have just a 3 left. So we can select a subarray of just that 3 with obviously no more elements to choose and set that equal to 0. So intuitively, you can get this sense that each unique number in this input array is going to have to be the minimum in some subarray. But the question becomes, how can we optimize this so that we remove the maximum number of instances of each minimum element? How do we know that we can include the one at index 1 and the one at index 3 together, right? So this example will help us kind of illustrate that. If we're taking in each number one at a time, right? So starting at 1, this is the first time that we've actually seen the number 1. We know that that will serve as a minimum in some subarray, but we want to know, are there more ones in this input array that we can include in that subarray so that we can get both of them out in the same operation? And a way we can kind of keep track of if there's more ones further on in the array is let's use a stack. So we're going to keep track of the fact that we've seen a 1. Now, we're looking at the next number, which is 2. A 2 is greater than a 1. So at any point, that 2 can be included in a subarray with this 1, and that 1 will still be the minimum. But we know that 2 will later on in a different operation also need to serve as a minimum element. So we want to keep track of that, push a 2 onto our stack. But we want to keep searching because at this point, we've only seen numbers that are strictly increasing. If we keep this trend, or just looking ahead by 1, there could be more 2's further on. We want to know that so we can remove them again in the same operation if possible. Now we'll see a 3. Similarly, same logic, we're still considering the subarrays. We're still looking for 1's, we're still looking for subarrays with 2's. But now we see a 3. That's another unique number that we're going to have to include for its own operation. But we want to keep looking for more 3's. Now we see another 3, right? We're not going to necessarily push that 3 onto the stack, right? What this 3 on the stack symbolizes is that prior to what we're looking at now, prior to this 3 that we're looking at now, the previous maximum number that we've seen is a 3. So if we're looking at a 3 now, we know that that can be included in the subarray where the 3 is the minimum element. Things get interesting when we move on to the next number, which is a 2. Now, let's look at the top of the stack. We know that the previous maximum is a 3, and that 3 will have to serve as the minimum element in some subarray. But because now we see a 2, any subarray that includes this 2 and further, and also includes this 3, the 3 is no longer the minimum. So at this point, we know this is the cutoff, the end of when we can include a subarray with 3's. So as soon as we see a number that is smaller than the top of the stack, a 2, for example, we want to get rid of that 3. Now, we see the top of the stack is a 2. We're currently on a 2. That is completely fine because in this very subarray that's highlighted on the screen right now, you see a 2 here and a 2 here. We want to include those two together and remove them at the same time, set them equal to 0 at the same time. Now, moving on to the next number, we see 1. Again, at this point, this is another hard cutoff in the array for a subarray with a minimum value of 2. Because if we include this 1, that subarray's minimum is now a 1. So at this point, because again, the 1 is smaller than 2, pop 2 from the stack, and we're done. So the main keys to an algorithm like this is making sure to every time that you see a unique number that's greater than the top of the stack, or when the stack is empty because we have to push the first number on originally, to increase the number of operations by 1. Then as we continue to traverse the input nums, this continues, right? So if you keep seeing this increasing trend, that's operations that have to happen. But the second that you see a number that is smaller than the top of the stack, at that point we want to keep popping from the stack until that's no longer true. And then we want to just do this for every num in nums. Now we'll move on. So right away, I'm just going to define a list in Python which has built-in functionality to act as a stack. Then we're going to just want to keep track of a variable to know how many operations. So we're going to want to increase this again every time that we see a unique number that will serve as a minimum in some subarray. So we're going to want to iterate through nums, and the very first thing we're going to want to check when we see a new number is this smaller than the top of the stack? Does this break this increasing chain? Is this a cutoff point for some subarrays, right? So while the stack is not empty, and while the top of it is greater than the number we're currently looking at, we can just pop whatever element is there. Now, just based on the problem constraints, right, this is non-negative, so n could be 0. If that's the case, we don't have to do anything to that number because it already is 0. Now, if the stack is not empty, right? No, yeah, if the stack is empty, we want to just push numbers on, and that's a new unique number that is going to be a minimum. Or if the stack is strictly increasing at this point, so if the top of the stack is greater, no, less than the number that we're looking at now, this is a new separate operation that's going to have to be done, and we can add that to the stack. Now, as soon as we're done iterating over nums, we can just return the number of operations. That should do it. So we'll go ahead and submit this. Yeah. So you can see, just speaking time and space complexity, this is a linear time algorithm. We're just iterating over nums. That's all we're doing. Each number would be pushed and popped from the stack at least once, so this doesn't add any extra overhead or too much complexity you can see here. Well, yeah. In memory, this is O of n memory as well, because worst case, if a strictly linearly increasing array, we would push all n elements onto the stack.